Now we will solve a few more examples on kinematics before we move on to dynamics. A car travels due east with a speed of velocity of the car with respect to Earth 50.0 kilometers per hour. Raindrops are falling at a constant speed, velocity of the rain with respect to Earth, vertically with respect to Earth. The traces of the rain on the side windows of the car make an angle of 60 degrees with the vertical. Find the velocity of the rain with respect to the car and the Earth. Okay, so here's our car that is traveling due east with a velocity with respect to Earth VCE, and raindrops are falling vertically down with a velocity VRE with respect to the Earth. And you can see that I have two reference frames, car reference frame and Earth reference frame. The Earth reference frame is fixed. The car reference frame, that is, there is an observer in the car. The car reference frame is moving at a constant velocity VCE with respect to the Earth reference frame due east. So it's in plus I hat direction as I have shown here. So if you pick a point, then we report the position of this point with respect to the car and with respect to the Earth. You can see from this diagram is the fact that the position of the point with respect to the Earth reference frame, RE, is the position reported by an observer in the car reference frame plus VCE times T. T is the time that has elapsed from t equals 0 to time t. The car reference frame has moved a distance VCE times t. So if I take a derivative of this with respect to time, then if this is the rain that I'm talking about, then the velocity of the rain with respect to the Earth, the raindrop, it's going to be velocity of the raindrop with respect to the car plus VCE, because VCE doesn't have a time dependence. If I take its time derivative, I will get 0. So this is the Galilean transformation equation between the car and Earth reference frame when we are reporting the velocity. Now, what do we know about the velocity of the raindrop with respect to the Earth reference frame? It is minus VRE j hat. It's vertically down, and we know that the velocity of the car with respect to the Earth reference frame is VCE I hat because it's traveling due east. So if I plug this into the Galilean transformation equation, I will find that minus VRE j hat is equal to VCE I hat plus velocity of the rain with respect to the car. So you can see that the velocity of the raindrop with respect to the car reference frame is velocity of the rain with respect to the Earth reference frame minus velocity of the car with respect to the Earth reference frame. So that is what I obtained from the Galilean transformation equation. Okay, so if I show this on a diagram, you can see velocity of the car with respect to the Earth is in plus I hat direction. Velocity of the raindrop with respect to the Earth is in minus j hat direction. And I have just found out that velocity of the raindrop with respect to the car is the difference, VRE minus VCE. So that means I go from the tip of VCE to the tip of VRE. That is the velocity of the rain with respect to the car. And as you can see, it makes an angle theta with respect to the vertical axis, which is 60 degrees. Now, what is the magnitude of the velocity of the rain with respect to the car? As you can see from this diagram, it's going to be square root of VRE square plus VCE square, and the angle theta has a tangent that is VCE divided by VRE. So velocity of the rain with respect to the Earth reference frame, VRE, is VCE divided by tangent theta, which is 50.0 kilometers per hour divided by tangent 60 degrees. So this tells us that the velocity of the rain with respect to the Earth has a magnitude 28.9 kilometers per hour, and it is vertically down. This was given in the problem. So this is the velocity of the raindrop as reported by an Earth observer. On the other hand, the magnitude of the velocity of the raindrop with respect to the car is square root 50 square plus 28.9 square. This gives us roughly 57.7. So we can report the velocity of the rain with respect to the car reference frame to be 57.7 kilometers per hour with a direction that is 60 degree west of vertically downward direction. So this is what we report for the velocity of the raindrop with respect to the car. Okay, so we have a car that is traveling due east with a speed 50 kilometers per hour, and we have two observers, one in the Earth reference frame. So this is the Earth reference frame observer, and this is the car reference frame observer, and they are looking at the raindrops. The raindrops are falling at a constant speed VRE vertically downward with respect to the Earth reference frame. However, the person in the car sees that these raindrops are making an angle 60 degree with respect to the vertical by looking at the traces of the rain on the side windows of the car. So this is a side window of the car, and we see that the raindrops are making an angle. So what is the velocity of the rain as reported by the Earth and the car observer? Well, we have found the Galilean transformation equation for the case where I have a constant velocity with respect to the Earth reference frame in the I-hat direction due east, and I see that the position vector transformation is RE equals RC plus VCET, where VCE is a constant vector. So we have the velocity transformation, VRE is VRC plus VCE. Now, plugging in minus VRE j hat for VRE vector and VCE is VCE I hat, we see that the velocity of the rain with respect to the car is the difference between VRE and VCE, and so you can see that it's going to make an angle theta with respect to the vertical, which is 60 degrees. So the VRE is basically VCE divided by tangent 60. Tangent 60 is VCE over VRE. So we can find the magnitude of the raindrop velocity with respect to the Earth observer to be 28.9 kilometers per hour, and it's vertically down. And VRC magnitude is square root of VRE square plus VCE square using Pythagorean theorem. So that is 57.7, and we already know it's 60 degrees west of vertically downward direction. Okay, let's move on to the next example. A bolt is dropped from rest in an elevator of height h and upward acceleration a. When does it hit the floor? Solve both in the earth and elevator fixed reference frames. Okay, so we have an earth reference frame which is fixed, the elevator reference frame that is accelerating with constant acceleration a in the upward direction. So you can see that it's in plus j hat direction, and as time goes by we have a separation between the origins of elevator and earth reference frames, 1/2 at square. So we can find Galilean transformation equations. So the position vector reported by the Earth observer, RE, is the sum of the position vector reported by the elevator observer plus 1/2 at square. And therefore, if you take a derivative twice, you can see that the acceleration reported by the Earth observer is acceleration reported by the elevator observer plus a. So this is taking the derivative of position vector twice. So we do with respect to time, d squared dt squared. Okay, so let's solve this problem in the elevator fixed reference frame. So in the elevator fixed reference frame, the original position at t is equal to 0 for the bolt is h j hat. And the final position in the elevator is 0 j hat. So we have a change in the position. The acceleration in the elevator reference frame is acceleration in the earth reference frame minus a due to our Galilean transformation equation. And what is the acceleration in the earth reference frame? Well, we have the gravitational acceleration g here. So we can see that this is going to be minus g minus a, which is minus g plus a j hat. So g is our gravitational acceleration. Okay, so we can basically see that this is going to be a constant acceleration motion in the elevator reference frame. Constant acceleration motion. Maybe I should write this. Okay, so this is correct. Or let's make sure that this is written correctly. Acceleration in the earth reference frame is minus g j hat. So it's going to be minus g minus j hat minus a vector, which is minus a j hat. Okay. So this is going to be minus g plus a j hat. The total displacement we have in the elevator reference frame is h, so that's the distance we travel, and we travel this distance with a constant acceleration g plus a, so it's going to be 1 over 2 g plus a t final square. Therefore, we find that the final time will be 2h divided by g plus a square root. Now we can take a look at it in the Earth fixed reference frame. In the Earth fixed reference frame, our position at t equals to 0 is h j hat, and our position in the final time t final is 1 over 2 a t final square j hat, because that's the distance the elevator travels. It's at the bottom of the elevator with respect to the earth. It's 1 over 2 a t final square j hat. So the displacement we have according to the earth reference frame is 1 over 2 a t final square minus h j hat. The acceleration in the Earth reference frame is minus g j hat. So we can see that this is also constant acceleration motion on this reference frame. And then we can see that the displacement we have, delta RE, will be equal to minus 1 over 2 g t final square j hat. It's the integral of acceleration with respect to time twice from 0 to t final. Okay, so we can see that the displacement we have 1 over 2 a t final square minus h j hat is equal to minus 1 over 2 g t final square j hat. Therefore, h can be seen as 1 over 2 a plus g t final square. Therefore, the time it takes is 2h divided by a plus g square root. So we can solve this problem from Earth point of view and elevator reference frame point of view. We have the elevator moving with constant acceleration a with respect to the Earth observer. At t equals to 0, I think the elevator and Earth reference frames have the common origin. And as time goes by, the origin of the elevator reference frame moves a distance 1 over 2 at square. And we can see the Galilean transformation equation that tells us the acceleration in the Earth reference frame is acceleration in the elevator reference frame plus a. So in the elevator fixed reference frame, I have to find the initial position and final position. Initial position is hj hat, final position is 0 because the bolt has dropped to the bottom of the elevator. The acceleration in the elevator reference frame is acceleration in the Earth reference frame minus a vector, which is minus g plus a j hat. So I can see that the distance I travel h must be equal to 1 over 2 g plus a t final square, because that is the acceleration I see, g plus a in minus j hat direction in the elevator. So this is going to give me for t final square root 2h over g plus a. When I solve it in the Earth reference frame, at t equals to 0, my bolt is at hj hat, at t equals t final is at the bottom of the elevator, where the bottom of the elevator has moved a distance 1 over 2 at final square in the plus j hat direction. Therefore, my displacement is 1 over 2 at final square minus h j hat. The acceleration in the Earth reference frame is gravitational acceleration minus gj hat. So you can see that delta RE basically, first I find delta VE, which is the integral 0 to t minus g j hat dt, which is minus gt. And then I find the displacement delta RE, which is going to be integral from 0 to t, so this is going to minus gt j hat, minus gt j hat dt, which is minus 1 over 2 gt square. So this is 0 to t final. Therefore, this will be my displacement in the Earth reference frame. So the displacement 1/2 at final square minus h is minus 1 over 2 gt final square, which gives me the same answer for the time it takes for the bolt to drop to the bottom of the elevator. Now, as a final example, a particle moves with a velocity v related to its position x by v of x is equal to a divided by x, where a is a constant and it's starting from, the motion is starting from the origin x equals 0. first find the dimension of a, then find acceleration a of x, position x of t, and velocity v of t, so as functions of position and time. Now, since the velocity of the particle has a relationship with x, a over x, the dimension of the velocity is the distance we travel per unit time, L divided by t, that is the dimension of a divided by dimension of x, position. Dimension of a is what I'm trying to find. Dimension of position is length. So you can see that the dimension of a is L squared divided by t. So m, l, and t are fundamental quantities in mechanics. So we have to write it in terms of these three. So it's L squared over t for the dimension of the constant capital A. What is the acceleration? Well, acceleration is related to velocity. It is dv dt. A is dv dt. And because the velocity is a function of position here, it's going to be dv dx dx dt. Okay? And what is dv dx? We take a derivative of a over x with respect to x. It is minus a divided by x squared. Dx dt is my velocity, v. So it is minus a over x squared times a over x. So I find that acceleration can be written as a function of position as minus a squared divided by x cubed. Now I want to know velocity as a function, I want to know position as a function of time. The velocity is dx dt, which is a over x. So you can see that this means x dx is equal to a dt. So if I integrate this from 0 to time t, x dx integral from 0 to time t a dt, I will find x squared over 2 at time t minus 0, which is x0 squared over 2, and the right hand side is at. Well, this is going to be 0 because I'm starting from the origin. The motion starts from the origin, so I can see that x of t is square root 2at. So the position can be written as a function of time. Finally, I want to know velocity as a function of time. So I just take another derivative of the position. So velocity as a function of time is dx dt, which is the derivative with respect to time of square root 2at, and this will be 1 over 2 t to the power minus 1/2 square root 2a, and that will give me, for the velocity as a function of time, a divided by 2t square root. Okay, so this was a good exercise to find all the kinematic quantities in terms of position and time. Given that velocity is given as a function of position as a over x, first we found the dimension of a, knowing the dimension of v and x. Dimension of v is L over t, dimension of position is L, so it's L squared over t. Now, using the relationship between acceleration and velocity, a is dv dt, v is a over x, but x is a function of t, so it is dv dx dx dt. dv dx is minus a over x squared, dx dt is v, so we can find acceleration as a function of position minus a squared over x cubed. We can find x as a function of t using v equals dx dt, which is a over x, by integrating this x dx and a dt from time t equals 0 to t. That gives us the value of position at time t squared divided by 2 minus the value of position at t equals 0 squared divided by 2. The position was origin at t equals 0. So it's x squared over 2 equals at. X is 2 square root 2at. Then if we take a derivative with respect to time of the position, we find the velocity as a function of time, which is square root a over 2